first. So I've been asked about this homework problem, so I'll start class with this. And the key to the problem is you need to focus, okay? I'll leave it up there the way it's written. So you're asking what happens as x goes to infinity of this expression. So let's just take a look at the numerator. We have infinity squared times 2 is still infinity, plus 1, infinity and squared, infinity. So the top is infinite. The bottom, infinity times infinity. So infinity over infinity. Don't really know what happens there. Go ahead. Were you going to?
Oh, no, I was legit. Sorry.
So were you asking this because you were trying to find like a shorter way of doing it? Or, okay. What you could do is you could realize that when you expand all this out, right, multiply it out, the leading term of that is this, right? And then you have plus, and there's a bunch of other junk, but you're saying all of those would be dominated by x to the fourth. I agree with that. So that really wouldn't matter. This one right here, when you multiply this out, x minus 1 squared, the leading term there would be x squared, then some other stuff in parentheses. And then this one right here is x squared plus x. When you multiply these two together, you would have what? X to the fourth. So you have a 4x to the fourth plus something. And then on the bottom, you have an x to the fourth plus some other stuff here. And I think your question is, can you just look at those two? Is that what you were getting at? Yeah, pretty much. I mean, with this particular problem, because it's polynomials, you can do that. And then, come through. Did you still multiply top and bottom by like x, 1 over x to the fourth? Or did you just look at the coefficient? If it's polynomial over polynomial, yes. If these two powers match, then it's just going to be 4 over 1, which is just 4. So that would be acceptable, okay, But you should be comfortable coming in with that special thing if it's not a polynomial. Does that answer your question? Okay. Anyone else have any questions over any of the homework? No?
I have a question on one of them, but I don't know the problem off the top of my head.
Okay.
It's one dealing with the ax minus bx.
Oh, yeah.
AX minus. Did y'all get my email not to do number 41?
Yeah.
Okay.
I think it was number 26.
Yeah.
So root x squared plus ax minus.
Wait. Say again. It's a limit?
Yep, limit x squared to infinity.
Okay.
Root x squared plus ax
Root x squared plus ax.
minus root x squared plus bx.
Did anybody get this one? Yeah? So how did you do it? So you did a conjugate? You did a conjugate, yeah. So if you plug infinity in, you have infinity squared. This is all infinite minus this will become infinite. So you have infinity minus infinity. And that is an indeterminate form. This is something we don't know what this turns out to be, so we have to do some sort of algebra. And so the technique is to come in here and multiply by a 1, but the one that we use would be the conjugate of what you see here. And my memory is not real good. I don't know if it's an age thing or I've just partitioned certain parts of my brain off for other things, but I believe it was Edward, right? Were you the one who told us conjugate last class? Who was it, Bailey? Was it Bailey? Someone was sitting right in there, right? Said conjugate, okay. So this is the same exact setup. And then we just looked at this as being over 1. But this has to be a 1. We can't just throw the conjugate up there. It has to be a 1, so we have to put it like that. And now when you multiply out the top, you should get, what, this root and this root. The roots go away.
Yeah.
And so you have limit x goes to infinity of x squared plus ax. And by design, the next two terms should cancel each other out. So I won't even write those down. Then you have the last ones, these two together. And just be careful here with your signs, because the two roots together are going to make the root go away, so you'll just have x squared plus bx. But it's a negative, because it's positive times negative. So you have minus x squared, and you could put plus bx and then put it in parentheses, or you could distribute the negative now. It's up to you. Understand? And then that's still over this conjugate. That doesn't look very nice. Okay. Equals limit x goes to infinity. So upstairs here, what goes away? X squareds are going to cancel, and you'll be left with ax minus bx. Ax minus bx over, down here, the conjugate. Is this the part where we're kind of stuck now? So I'll do a quick check here, to try and see what happens as x goes to infinity. This becomes infinite, right? Minus infinity, you don't even know what that is, right? You don't know? And then down here you have infinity plus infinity. So that'll be infinity. So you've got something you don't even know over infinity. So any ideas on what we can do here? Yes?
I did the 1 over x and pull it out and put it on top and put it back in.
There you go. So trying to look at the highest power of x in here, and we actually have the same thing in here. Let's make that turn into a 1. So I have to divide it by x squared, but I have to start outside the root, so I come in with a 1 over x. I do it on the top and bottom, 1 over x. That way when it goes in the root, it gets squared on its way in. We talked about that last class. So I'm going to introduce a 1 over x here and a 1 over x here and pass it through both of the roots, and I'll do that on the next step. So this becomes limit x approaches infinity. All right, what happens in the numerator?
It's just a minus b.
A minus b over. Now, this 1 over x has to go into this root and into this root, right? Because it's distribution, two terms here. So when it goes in here, it becomes 1 over x squared, and it turns this x squared into a what? A 1. And then you have plus ax over x squared. Remember, when it goes in, it gets squared on its way in, right? So it becomes a 1 over x squared, turns into a 1. Ax over x squared is what? A over x. And then plus, now the same exact thing happens here. What happens when it goes in? First piece? Okay, so it gets squared, becomes x squared over x squared, which is 1. And then this one will be plus b over x. Am I addressing the question here? Is this okay? Now let x go to infinity. And what happens?
Is it just a minus b over 2?
This goes to what? 0. This goes to 0 because you have a fixed number over something becoming infinite. That squashes down to nothing.
Yeah, that's why I stopped, because I know it was a fixed number, but I didn't know anything about letter. So,
Yeah, it's a and b are constants, so they're constant. They're numbers, but they're not changing. They're stuck. So that's going to go to 0. So you have a minus b, right? A minus b. I've already taken the limit, so I don't need to write it anymore. That went to 0. So I have root 1, root 1. Root 1 is 1, right? So this is 1 plus 1 is 2. A minus b over 2. That's the limit. Questions?
So you can't plug the limit in for A and B because it's two different.
It's not like,
It's not X.
It's not X, that's right. A and B are not changing. Yeah, they're fixed, they're static. Like if we wanted to, we could have replaced A with 5 and B with 3 in the problem. And then our answer would have been what? 1, right? 5 and 3, the answer would have been 1. But they're just numbers that don't change throughout the entire problem.
I was
Yes?
just gonna ask, I'm pretty sure it's just, I just forgot. If there was like an x cubed underneath the root, and you took it out, it'd be 1 over x squared, right?
If it was just, wait a minute. If you had x cubed under a root,
And you took it out to,
you want me to take something out?
yeah, take it out, so it'd be 1 over x squared?
I'm not sure what you mean.
Like, you know how we had x squared underneath?
Yes.
On the problem, we took the 1 over x out?
I didn't take 1 over x out. I came in with this myself.
Okay.
I said, what, see, what I was thinking was, what, I thought you were the one that told me to put 1 over x. No?
Yeah, I did, but
Okay.
I'm talking about like it was x over cube, or x cubed.
Okay, so you look at x squared and you say, what do I need to make that a 1? I need to divide it by x squared. So if I bring a 1 over x out here, then when it goes in, it becomes 1 over x squared. Okay, now if you, I think what you're saying,
Matter. Okay, I see what you mean.
if you would have had this x cubed in there plus some junk, then what would you put in here so that when it goes in, it becomes an x cubed? This one's a little harder. 1 over x.
I thought it was 1 over x, when you pull it in, you go 2.
Well, if that goes in, no, because that would need a cube root out there. Then it would get cubed on its way in. So what would that have to be?
1 over x squared.
Would it be 2/3?
2/3. So what's going to happen if it squares on its way in? I'm going to raise this up. This is a good question. If you had this, and you're trying to come in with a 1 over x to some power, what do I need it to be so when I put it in there, it's 1 over x cubed? Okay, so you want this, right? You want 1 over x to some power. I'm going to call it m. I want that when I square it, it becomes what? 1 over x to the
4/3.
third power, right?
Can be
Yes.
1 over x to the 4/3.
4/3? You want this to be 4/3?
I think it's less than that.
Well, let's see if you agree with this. We'll see if it's 4/3. Do you agree with this? When it goes in, it gets squared. Yes? So once it goes in and gets squared, I want it to turn out to be that, right?
Yeah.
Okay. Now, let's just put squared on top and bottom here. 1 squared is 1. What's x to the m to the second power? X to the 2m. You need x to the 2m to be equal to x to the 3. What does that mean? 2m has to be equal to 3, right? So 2m has to be equal to 3, so m has to be 3/2. I think someone said 2/3. It's the other way. It's 3/2. So let's just double check it. If I put this 3/2, then when I square it, right, I double this number. What's 3/2 times 2? 3. Now that, I don't foresee this happening,
Okay.
but you asked the question,
I started
so
looking ahead in the book and I started realizing like, oh man, I don't know that.
yeah, it could get ugly. And then imagine, if this was 5th power and that was cube root, then you have to really start thinking about what you need. I've seen other approaches to this, other ways of doing it, but okay. Let's get down to business. So my first announcement, I need to take a vote, a poll here. There's a very good chance, probably about 95% chance, that Monday I will not be able to hold class. So we have two options. We can have a sub come in and do the class, or I can give you a set of videos to watch and then you do your homework based on those videos. Those are the two options. So you're You're already voting? Yeah. Or do you have a question? I don't know who the sub would be. That's the thing. I don't have any control of that. I would just request a sub, and they would try and get someone to cover it. So how many of you are in favor of, let's do the videos first. How many of you think you would just do the videos? Okay, I think that's
Your
overwhelming.
videos, like your course videos?
Well, I already sent an email. Anyone check their email today? Okay, I already sent an email, and it says I may not have class on Monday. I'll let you know by Saturday at 8 p.m. I will send an email out through Canvas saying either I'm going to have class or not. If I don't have class, then it shows the assignment. It's watch this video, which is a course video on continuity, and then it's a lecture video on continuity, and then it's go do your homework. But continuity is one of those sections that's a little weird. That's what I was supposed to do today. I'm deciding to skip continuity and get into chapter 2 because I think continuity is one of those things where you can kind of, you can live with just knowing what it means without having to get too deep into the algebra of it. So I want to see how you do with the videos.
What video were we supposed to watch this last time? I watched the derivative one.
Good. That's what I'm going to cover this time. Yeah, I don't think I told you which one to watch. I didn't tell you because I wanted you to focus on your homework. I think that's what I had said. Focus on your homework. Okay, so today we are going to start chapter 2. Were there any other questions on the limits stuff right now? I mean, we're going to still have limits. There's going to be more practice, but nothing? All right, so let's talk about this. So if you were to describe calculus 1 is called differential calculus. That's what you're taking right now. So you talk about, you talk to someone who's at a different college and they're like, oh yeah, I'm taking differential calculus. You're like, ooh, that sounds fancy. It's the same thing you're doing right here. Cal 1 is differential calculus, okay? And then Cal 2 is called integral calculus. Integral calculus. And then beyond that, like a Cal 3, some schools have Cal 4, is like vector calculus, which is just higher dimensional calculus. That's all it is. It's calculus in 3-dimensional space or 4-dimensional space using vectors instead of everything we do is pretty much flat sheet of paper stuff, right? Function on 2-dimensional space. Also, if you ever hear of a school that has Cal 1, 2, 3, and 4, don't think that it's like, oh my God, they have 4 calculuses. It's usually, the calculus sequence is usually 3 4-hour courses, 3 4-hour courses, or 4 3-hour courses. That's usually what it is. So there are schools with Cal 4, or that have a Cal 4, but it's really the same material, but they break it up at different places instead of, yeah, so just FYI. All right, so differential calculus is what we're studying, and the word differential comes from the idea of this thing called the derivative. So all of Cal 1 pretty much comes from that one chapter right there, chapter 2, derivatives. So it's very important is what I'm getting at. And then in Cal 2, integral, as you'll see if you ever take Cal 2, is that this thing of taking a derivative or finding derivatives or differentiating, all of these things, it's a process. It's a procedure. And in Cal 2, what you do is you go backwards. So you reverse the procedure, and it's much more difficult, but you reverse it, and that's called integration or integral calculus. So FYI. All right, so derivatives. There's a lot of words here, which I don't want to read this whole thing because everyone can read, right, I hope. But there's, what we've established so far is the limit. And what we've seen is that the limit is a pretty powerful thing. It allows us to figure out how things behave and not ever have to investigate the functions at a specific point where the function might not be defined. So it allows us to kind of weave our way around some pretty serious problems of division by zero and things like that. But there's one particular limit that comes up that's very important. So important, it's actually got its own name. It's called the derivative. And what it's all based upon is this picture of a tangent line to a circle. So if you remember from, do we want to kill one set of lights here just so we can see this a little better? All right, so if you recall, if you have a circle, right, the tangent line is a line that intersects that circle at one point. Right, so that green line hits at that blue point. If I were to zoom into that, right, zoom in, that green line would only touch one point on the circle, wouldn't it? And that's where the idea of tangent came from. If I have a second point on that graph, on that line, then I no longer have a tangent line, do I? And we call that a secant line. So the secant line passes through 2 points, whereas the tangent line passes through only one. Right? Okay. Now, does it make sense for us to talk about a tangent line on a function then?
Yes.
Well, I mean, it makes sense that we could at least entertain the question, right? So if I had 2 points on a curve like this, right, 2 points, I could say that the line connecting those would be kind of like the secant line was with the circle, right? It's not through one point. But if I take this second point over here, let's zoom down. Okay, sorry, let me zoom this out. There we go. So there's 2 points on a curve, right? If I take that second point and I move it closer and closer to the other point, so the black point's kind of like my base point, I'm not moving it, and the blue point I'm sliding towards it, then all of these are secant lines, right? All of these. If I stop, that's a secant line, that's a secant line. All of these are secant lines. But if I move it closer and closer and closer, the slope of that line starts to approach a specific value. Right? Would you agree the slope of that line is positive? And if I were to have been over here, the slope is negative, right? But as I get closer and closer and closer, how close? Well, arbitrarily close, really, really close. Then I'm approaching a true tangent line. If I put that blue point right on top of the black one, right? I will achieve this concept of a tangent line. There should only be one of them, right, for that point? There should only be one tangent line on that curve. So it would not make sense, hopefully you see this, it would not make sense to say, well that's also a tangent line. Or that's a tangent line also. There should only be one. Yeah? Do you agree? Now, does it follow the whole circle thing? With the circle, we said tangent can only hit the function at one point, right? That's what we said? Does this follow the same behavior? Well, let me zoom back out. Is this green line only hitting the function at one point? It looks like possibly as I continue up that way, I'm going to intersect that curve somewhere else, right? So what we do is we say, don't worry about what's happening in other places. It's almost like you're zooming in, zooming in, zooming in to a point that you're only looking locally, like in a local region. And as long as you're hitting it in one point in that local region, then it makes sense to still use the word tangent. Okay? All right, so we continue. How do we actually come up with a tangent line? Right? We've seen to get it, first we start with the point on a curve, that black base point, right? So we start with some point. I think I have a picture down here. I've already brought in all the crap. I should have reset this. Let me reevaluate this whole notebook. That way it resets everything. Okay. So I'm going to draw my own picture up here, and then I'll come up here and do it. So we start with a curve. We have some curve. We start with some initial point, right? Select some other point on the curve, anything we want. Then draw a line between these 2 points, and that is our secant line. Then slowly move the second point closer to the first one. So imagine that this is x. Then this point over here, I can call it whatever I want. I can call it y, I can call it m, I can call it anything, right? But how about calling it x plus h? Wouldn't that be whatever x is plus a little bit more? Assuming that h is a positive number here. Then to slide this point over, right, I would need h to become what? Smaller, right? And eventually 0. Yes? Okay, so I move it. When the 2 points are on top of each other, we get the tangent line. So now with a little bit more better labels, we can actually do this with this picture. So we have a first point, there it is. I call it x1, y1. And for this example, I actually know the values, -1 and 2. Then I have a second point, there it is way down there. I call it x2, y2. I draw a secant line between them. Where the hell is my curve? Where's my function? Where's my function? There we go. So I don't have the function up there. I'm not sure where it went. But if I have this, right, if I have 2 points on a line, I can always find the slope of that line, can't I? Just rise over run. Can always do that. So when it comes to this secant line, I can always find its slope, right? So here's a particular function. So I'm actually giving you this function, 3x cubed minus 5x. I'll write the function up here so that we have a reference to it. And it looks like that thing over there. Whatever. So what we're going to do is we're going to find the equation of the line through these 2 points. Right? That's what we're going to do. -1, 2, and 1, -2. -1, 2, and 1, -2. Let's first verify that both of these points live on this curve. Let's just verify it. So if I plug -1 in here, what do I get? So what's -1 cubed? -1 times 3. -3. What's -5 times -1? 5. So this is -3 plus 5 is 2. So that point does live on my curve, right? And this point, plug in 1, you get -2. So both of them live on the curve. I'm not sure where they are relatively, so let me just plot them for you. There they are. Okay, so one of them's up here, one of them's down here. Let's find the equation of the line through them. The equation. So how do you find the equation of a line? What do you need to find the equation of a line? Slope and intercept, or you can also use what's called the point slope formula. There were 2 formulas we had for the equation of a line if you're given 2 points. So the one that we're going to use is this one. No, we're not going to use that one. Y minus y1 equals m times x minus x1. This is called the point, this is called the point slope formula for a line. So in order to come up with the equation of a line, you have to have at least 1 point on the line and the slope of the line, don't you? Do we have a point?
Yes.
Absolutely. We have 2 of them, actually. But I'm just going to use this one right here, -1, 2. I'll call that my x1, y1. OK, so I have my point. x1 and y1, I've got it. All I need now is what?
Another point.
In this formula, I don't need the other point. But I do need the slope, though. How do you find the slope of the line? So m is the slope. Rise over run. The definition of m, rise over run, would be y2 minus y1 over x2 minus x1. This is from college algebra, right? This is our formula for slope. So let's just see. We already called this point here x1, y1. Yeah. So this right here we call x2, y2. and then just plug them into this. So let's go ahead and do it. What's y2 for us here? Negative 2 minus what's y1 for us? 2. And then over x2, which is 1 minus negative 1. So what do we get here? Negative 4 over 2, so negative 2. So the slope of this line is negative 2. And we have a point on the line, so we have everything we need for the equation, yes? So let's write the equation down. The equation of the line connecting those 2 points should be y minus, what was my y1? I just erased it.
2.
It was 2, positive 2? Yes, okay. Oh, I put it right here. And then equals m, which we just found to be negative 2, times x minus x1, which was negative 1. And now if I just clean that up, that's the equation of the line that goes through those 2 points. There's no calculus here. Do you all agree? There's nothing calculus here at all. It's all algebra at this point. So this will become what? X plus 1 in here? And then distribute through. So negative 2x minus 2. And bring your 2 over, and you'll have your nice form of a line. Y equals negative 2x. That's it. If I graph this line, it should hit this curve at those 2 points. So it's that line right there. Oh, it went through the origin. That's pretty good, right? That makes me feel better because doesn't this line go through the origin? What's its y-intercept?
0.
Plus 0, right? So it goes through, so I feel kind of good about that. So our rise over run, this is just showing you what the rise and run were. There's the equation of the line, negative 2x, we're done, all right? But, I mean, if that were the case, then what in the world are we here for, right? Like, why are we doing this? We need to come up with a general formula. All right, we're going to try and come up with a general formula. And what we're going to do is we're going to do this in a more arbitrary fashion. What I mean by that is instead of using x1, y1, x2, y2, like we did before, I'm going to use some different labels. So the labels I'm going to use are right up here. I'm going to use for x1, y1, instead of that, I'm going to use a, f of a. Because isn't f of a the y value when you plug in a? And then for x2, y2, instead of using that, oh, you know what? Did I do these backwards? No, this is the right way. Okay. X, f of x. I'm choosing to change the way I'm indicating things to you. Now I'm going to draw a picture, and this time forget the function we were just dealing with, right? Forget it. Let's just act like we have some arbitrary function. And I'm going to just draw it. I really don't know what it looks like, okay? I have no clue what this looks like. But I'm going to place here, I'm going to call this A. Come up here, right? This is the point A, f of A. Ugh. Do y'all see that? Is that okay? This is A, f of A. That's that point. And then I'm going to pick some other point over here, which I'm going to call x, because that's the other x coordinate, right? And it goes up here to some point on this graph, and that has the coordinates x, f of x. Y'all still with me? Okay. First of all, what's the slope of the line through those 2 points? What's the slope of the line? So what is the slope?
F of x minus f of a.
F of x, so it's y2 minus y1. So f of x minus f of a. Do you all agree with that? Everyone? Yes? Over x minus a. So regardless of the function that anyone ever gives me, right, I can always define the slope, the slope of the line connecting these 2 points with that equation right there. That's what the slope will always be.
But you have to know the function.
You would have to know the function, yeah, because I'd actually have to figure out what is f of x and what is f of x. Right? Everyone see that? Now, before we keep going, I want you to try and connect this to the calculus. The whole point of this was to try and move this point on top of that point, right? If I move this point towards there, aren't I saying let x, not x equal a, but x approach a? Let x get closer to a? Like really, really close? Like a limit, right? Like a limit? Tell me what happens to this if I let x approach a. So what happens if that x becomes an a? Get f of a minus f of a, which is 0. And then if I let that be a, what is it? A minus a is 0, and we get 0 over 0. Which traditionally we would be like, can't do it. But we've already seen that 0 over 0, if we do algebra appropriately, we might be able to actually get a number. And that's how we actually will be able to move this over here. We know that there's a tangent line. We know it's there. We just actually have to be able to find it. And it's always going to reduce down to that right there, that in a limit form. All right? So let me get back to this. All right, so we got our arbitrary points. So this slope right here, I have my cursor right here. Okay? This is what we call MSEC, meaning the slope of the secant line. As not to confuse it with the slope of the tangent line. Slope of tangent line would be different. I'll show you in a second why, how. So if this is the slope of the tangent line, then can't we actually come up with the equation of the tangent line? I got to leave this up here. Using that same formula we just had, equation of, did I say tangent? I meant secant. Can we find the equation of the secant line? Correcting myself. We have the slope of the secant line, don't we? Can we find the equation of the secant line? Well, in terms of this, we can. Using that same formula from college algebra, it's y minus, what's y1 for us? F of a equals m, what's m? F of x, write it down. It's what it is. Can't change what it is. Okay, that's your slope times now x minus a. Y minus y1 equals m times x minus x1. This was our x1, y1, wasn't it? So this equation right here, what this says right here, this is the equation of the secant line. You give me a graph, you give me a function, I don't care what it is, I can always come up with a base point and some other value. I can always find the equation of the line through those 2 points, right? Using that formula right there. No questions? Okay, so how do we get the tangent line? We just said, if we have the 2 points, there's AF of A, here's the second point, I draw the line, that's my secant line, I slide that point over, right? I slide that point over, and then voila, I'm on top of it. Uh-oh, shit, we have a problem, right? Because we have division by 0, don't we? We already said that. Once we let x be a, we have division by 0. It's undefined. So in order to get around this, all we're going to do to get around this issue right here of getting 0 over 0 is we are going to replace it with a limit. And what we will do is define the slope of the tangent line to be just a slight modification of this. It is what we get when we let the x approach a. So you see that's the only difference between the 2 formulas? Right here? Is a limit in front? That's it. So if I'm trying to define the tangent line slope, it'll just be that formula with this limit in front. I was just about to say, if this limit exists. If the limit doesn't exist, then I cannot define the slope of the tangent line. It won't be possible.
So that's the formula for a tangent line.
This is the formula for the slope of a tangent line at a particular point A. So you have to remember A is like the base point, and we're sliding x towards it. So this would be the slope of the tangent line at A, at x equals A. See, because if I give you a function, right? I say find the slope of the tangent line. You first have to tell me where you want me to be. Like here, pick that as A. Okay, right there. Now find the slope of the tangent line there. You could have said, okay, pick something over here. I'll call it A again, but that would be a different value. That would have as a different tangent line, wouldn't it? Like the slopes would not have to be the same. Yes?
Yes.
Okay. They look exactly the same, but they're not supposed to. Okay, so we have a way, we think, of finding the slope of the tangent line if we can do this limit. So we take the tangent, we've already said this. Now, if we can find the slope of the tangent line using this formula, then shouldn't we be able to come up with an equation for the tangent line?
Mm-hmm.
And it would be this equation with what?
Limit.
A little limit. Stick a little limit right in there, right? That limit, and then it becomes the equation of the tangent line. So I'm not going to write it down because it's right here. There, that's it. Well, I guess I will write it down. Because this is a pretty important formula. The equation of the tangent line at x equals A is y minus f of A equals limit x approaches A, f of x minus f of A over x minus A times, I'm going to run out of space, but times here, what, x minus A? So that goes right there. That's the big daddy formula right there. Does everyone see this is just a slight tweaking of algebra, like what we've seen in algebra, except now we have the idea of the limit, which allows us to get around that 0 over 0. I don't know why my code is sitting here. All right, so let's do a couple of problems. Let's see, what are we paying? Okay. Can we hit the lights? Get all the lights back up. Thank you. All right, find the equation of the tangent line to the function y equals x cubed minus 3x plus 1 at x equals 2. So we can graph this, right? This is a polynomial function. We could have the computer graph that for us, couldn't we? And what we're going to do is we're going to try and find the equation of the line that touches that graph at a single point, right? With an x value of 2. So if we need the equation of the tangent line, we may as well make sure we have the formula written down, and that way we know everything that we're going to need for it. So the equation, the formula that I just gave you was y minus f of A equals limit x approaches A, f of x minus f of A over x minus A times x minus A. So we need to know what A is, don't we? What's a for us? 2. Okay? At x equals a. So this number right here, for us, a is 2, right? That's telling you, this right here, x equals 2, is telling you, like wherever your graph is, it's telling you where to be and go to. And then what we're going to do is pull a second point into it. But that's the base point. So that always has to be given to you in some sense. Understand? Okay, now, what other piece of information am I going to need in here? What's something else I can actually evaluate here? F of a, right? Can I figure out what f of a is?
Sure.
So plug a into this. Now, we didn't call this f of x, but didn't we always say like y is f of x, right? Okay. So what would f of a be? That would be the same as f of 2. So plug 2 into the function, and what would you get? 8 minus 6 plus 1, so 3? You get 3. Yes? So this point right here is actually the point 2, 3, isn't it? And then what I'm doing, what this formula allows me to do right now is actually pick some other point out here, x, and then slide it towards it. That's what the formula is going to allow me to do. Any questions, though?
With the top part, you plugged in 2.
Yes. Plugged it into this, into the function. So just replace your x's with 2's. Right? 2 cubed is 8. Minus 3 times 2 is 6. So 8 minus 6 is 2 plus 1 is 3. We good? Okay. All right, so do you agree that the parts that I have from this right now, I do know what this is? Yes? I do know what this is. I never need to figure out what x is, and I never need to figure out what y is, because those will always be in the equation of a line, right? X and y will always be in there. But I do need to resolve what the slope is, and that's the whole part, that's the calculus. This is the calculus part of the problem. So on a separate side note over here, I'm still trying to figure out things. I need to figure out what is the limit as x approaches, now what is a? 2 of f of x, which I'll replace f of x in a second, minus f of a, what's f of a? 3 all over x minus 2. Understand? But what is f of x? It's this, right?
Yeah.
It's this.
You just plug it in.
So let me plug that in. So this becomes limit x approaches 2, f of x, which is x cubed minus 3x plus 1. But then what? Minus 3, and then over x minus 2. Y'all still with me? Okay, now, at this point, let's clean that up a little bit. The limit as x approaches 2 of x cubed minus 3x, what? Minus 1 over x minus 2. If I can figure out that limit, then I know the slope of the tangent line, don't I? What happens if I just try direct substitution on that limit? Do I get 0 on top?
Yeah.
Is it 8? Hold on. Oh, hold on. This was a minus 3. Thank you. Okay, hold on. I just caught this. This was minus 3. My fault. This, right, minus 3. I don't know why I wrote down minus 2. I had a little panic attack there, because this should be what? 1 minus 3 minus 2. We should be getting 0 over 0. Right? Does everyone see the mistake I did? I didn't put down, I put minus 3 and then I put minus 2 for some reason. I think I had already done it mentally, like I had done the 1 and the negative 3 together or something. Okay, now what is this limit? 0 over 0. So what happens when we see 0 over 0? we realize we have to do something, right? Trig or algebra? Can you factor that though? It's not a quadratic.
You're missing x squared.
I'm missing an x squared. What's that?
Can you plug it in?
Plug in, how do you mean?
It could be synthetic division.
That's right. Either synthetic or long division.
One of them.
Either one. That's why I brought this problem up. Because in college algebra, you should recall that there is a way to factor polynomials that are not factorable with traditional techniques. And that's using synthetic or long division. Now, what would be a great candidate? I mean, we have to really kind of think about this for a second. You know that the top goes to 0, don't you? When you plug in 2. So would you agree that, I mean, it has to be that the top has a factor of x minus 2 in it. Then some other factors, you don't even know what those are. But the top should factor, and one of them should be x minus 2, because when I plug 2 in, I should get 0 over 0. Is it plausible that the top should have a factor of x minus 2? It should. So when we're going to go over here and try and figure out what the heck it is, I can either use long division or synthetic division using this potential factor, which really comes from down here also. So what do y'all want, long or synthetic? How many show of hands? How many of you know synthetic division? Okay. Long division? Oh, okay. So let's do synthetic. If you have never seen synthetic, then you're going to have to brush up on it. So with synthetic division, what I'm going to do is I'm going to take the numerator, which is this right here. I'm going to write down just the coefficients. What are the coefficients of the numerator? 1, 0, -3, -2. So I have a 1 in the place of the x cubed. I have no x squareds, -3 x's, and then -2. Now I think that x minus 2 is a factor of this. So what should I use out here for synthetic division? Plus 2, the opposite. If the factor is minus 2, then we use plus 2 out here. And what I'm hoping for is to get a remainder out here of what? 0. That's what I'm hoping for. And then these numbers here are going to represent my answer somehow. So I bring 1 down. If you've never seen synthetic division, 1 comes down. 2 times 1 is 2. Add down, you get 2. 2 times 2 is 4. Add down, I get 1. 2 times 1 is 2. Add down, I get 0. Yes, that's what I wanted. That's what I wanted. That way confirms that this is a factor. This is a factor of it. Where's the rest of it then?
You take the one less of like, wouldn't it be x squared plus 2x?
It's these three numbers are the coefficients of my answer. And so, and I start with 1 power less than what it started with. So if it started up here at x cubed, then this is going to be 1x squared, so I may as well just write x squared. 1x squared plus 2x plus 1. So that means that when I was sitting here saying, hey, I think that this has to have a factor of x minus 2 in it, but I wasn't quite sure what this is, I actually know what that is now. It's that. So this piece right here that was a question mark is actually the x squared plus 2x plus 1. And what's nice about that? If I could factor it, I can cancel it. And now I can take a limit, and I'm not going to get 0 over 0 anymore. What do you get?
9.
Get 9?
Yeah.
A number, yes.
What happens if you factor, well, no, you can't factor.
It wouldn't actually matter. We don't need it to factor, because all we needed was this to cancel, right?
What if it was factorable?
And you did it? That'd be okay. If you plugged in 2, you'd still get 9, even if it factored.
Okay.
The two things you get would multiply, and they would come up with 9. Yes?
It sounds like you're just going to have to use long division.
When is the only time you have to use long division?
If there's a exponent,
If the denominator is not linear. That's right. If this were x squared minus 4, you would be forced to use long division. But this is what makes synthetic division so useful is that it's quick. Synthetic division is just another way to try and factor something. And I don't know if you remember in college algebra, the thing with synthetic division when you used it is that you had to come up with this thing called the list of rational zeros. And you had to come up with all these different combinations of p and q and plus and minus and all that stuff, right? But in calculus, we actually have a real good idea of what to use, right? Because if we're getting 0 over 0, we know that one of the factors has to be this. So that really helps us. And we don't have to come up with this big, awesome list of things to do. All right, so all we've done so far is we have found the slope of tangent line. We found the other piece. I think we can plug everything in, right? Okay, it was, here comes the equation of the tangent line. It should be y minus, what was f of a?
3.
It was 3, right? 3 equals m, which was this whole limit, right? That limit x approaches a, blah, 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 all that stuff. And we said that was what? 9. And then x minus a, which was 2. And I'll clean this up. Y minus 3 equals 9x minus 18. Add 3 to both sides. Y equals 9x minus 15. Yeah. Okay, so I didn't prepare this problem before I came into class, so I'm going to test it. Do you mind killing lights again? Just there's a program out there that's free on the web. There's a bunch of free graphing things out there. I'm kind of partial to this one called WinPlot because it's free, and if you're running Windows. So I can graph this. So what I'm going to do first is I'm going to graph the original function, which was x cubed minus, what was it, minus 3x minus 1? Or
What, the original?
the original one? Plus 1. And I'm going to graph that kind of big. There we go. There it is. There's the original function, right? And I was supposed to go to the value of what? 2 on this graph? And we said that when we went to 2, we actually had a point. So now I'm going to have this thing give me a point. I want a point, an x and y coordinate. Go ahead and give me a 2, 3. No, that's not 3. 3, and we'll make it kind of big, and we'll make it solid. And we should get, there's our point, right? With me? I claim that we found the line that passes through that point that's tangent to that point. And so if I'm going to really, really be confident about this, I'm just going to type in the equation of that line, and hopefully it works. So I'm going to type in, please graph for me now, 9x plus 15. No, minus 15. If it does not pass through that point, I messed up, right? There it is. See it? So we found the line that passes through that point that runs tangent to that point. Yes?
What happens if you get a remainder on long division?
Then your factor, your selection of thinking that this was a factor would not be correct. But it has to be. Think about it. If you're getting 0 over 0 when you're plugging 2 in, that means x minus 2 must be a factor. It's never going to happen. Now, if you do get a remainder, then you messed up your synthetic division because it's got to be 0. So you go back and run through it again. Like if you had forgotten that, remember how we had the 0 for the placeholder for x squared? If you had forgotten that, then you would have got a remainder. You'd have been like, what? What's going on? All right, y'all see that? That's kind of cool, right? I mean, we found the equation of that line that touches just at that point. This program actually allows me to, I can actually grab it and I can take my point anywhere, and it will actually show me the tangent line anywhere I want, and it'll actually compute the slope for me.